today as a speaker our postdoc, Isadora Veeren. So she did her undergraduate in Rio de Janeiro in UFRJ, Federal University of Rio de Janeiro, and she did her PhD at the Center, Brazilian Center for um, Research in Physics, the CBPF, and recently she joined the IEP. She will stay here for some time. So when she did her sandwich uh, doctorate in Germany, she met her collaborators, and she will talk about the work that they were doing together. Thank you very much.
Yeah, thank you. Thank you everyone for attending. So yeah, what I'm going to talk about here is some paper that we have already on archive on this collaboration that I did in Germany with some people. So the goal of this project was to find a way that when you have two people performing some kind of task and you can trust only one of them, you cannot really trust the other, how can you infer some kind of information about them? And in this case, how can I find out how many measurements this untrusted party is performing? And that's what we call a semi-device-independent certification. So to first talk about what I mean by device independence, we have to go back like roughly 100 years to the famous EPR paper by Einstein, Podolsky, and Rosen, where they formulate a criticism to quantum theory. Their argument is that quantum theory cannot be considered a complete description of physical reality. And their argument was initially formulated for momentum and position, but it can be also understood in terms of spin half particles in a way that we are more familiar with in quantum information. So the argument can be translated more or less like this. Suppose you have two distant parties, Alice and Bob, and each of them is going to get one particle of some global bipartite system. And this system is going to be on a singlet state like this. So zeros and ones are the eigenvectors of the measurement of spin along the z direction. And the thing is that because this state is perfectly anti-correlated, what you have is that if Alice measures on her qubit the spin along the z-axis, she knows for sure that if she gets the outcome +1, Bob's system must be on a state 1. It also happens that if she measures the spin along the z-axis and obtains outcome -1, then she knows for sure that Bob's system is on a state 0. And the same thing happens if, on the other hand, Alice decides to now measure the spin along the x-axis. So you can also, after some calculations, see that if she measures the spin along the x-axis and obtains outcome +1, she will be sure that Bob's system will be on a state plus, which is the eigenstate of the measurement along the x basis. And the other way around, if she obtains outcome -1, she also knows that Bob's state is on state minus. So what they argue in the APR paper is that, well, Alice can know for sure what are the values associated to Bob's measurements of spin along the x and the z axis without disturbing them. So they must correspond to what they call an element of reality. This is something that is intrinsic to the system, and it reveals something about the ontology of the system. The problem is that quantum theory predicts that since the observables associated to these two quantities do not commute, they cannot be simultaneously well-defined. So there's a contradiction there. And in the APR paper, they use this to argue that the quantum description of physical reality cannot be complete. And the way that this problem is described this way, you can trivially solve it by considering the so-called hidden variables. And the discussion around this, the solution to what they call the EPR paradox, is something that went on and on until it culminated in Bell's theorem. So what is a typical Bell scenario? What we can do now is consider that you have two parties, Alice and Bob, and I want to do this description in the most general way possible. So they share some state, rho, and Alice, in her lab, she's going to perform measurements, obtain outcomes, but the most general way I can think about it is in terms of a black box. So what Alice is doing is she has some black box. She has this box has an input X, which would be, for instance, a label for the measurement that Alice is performing, like she's performing a measurement of spin along the X or the Z axis. And this box is going to spit some number, a label, a classical outcome, which would be the outcome of a measurement. This is the most general way I can do this. And similarly for Bob, his box, which represents his lab, would also have some kind of input and some output. So if you want to describe this scenario, what you would have is a joint probability distribution of obtaining the outcomes A for Alice, B for Bob, given that the input that they put on their boxes was X and Y. Okay. So the thing is that in general, what you observe is that this joint probability, it does not factorize, which is nothing weird per se, because it just means these two quantities are correlated. Even though we are assuming that Alice and Bob are far away from each other and they don't have direct influence upon on each other, you could still understand the fact that these probabilities do not factorize as the influence of perhaps the past of the particles. They were prepared at some point before they were distributed between Alice and Bob. And these correlations could just be something reminiscent from this past interaction. So what you could do is consider now some hidden variable lambda that you don't have access to. But when you consider this hidden variable lambda that would be quantifying some past interaction, then the probabilities would factorize. Then if you consider a hidden variable, you would have the full picture and you would get what you expect, that the probability for Bob to obtain a certain outcome B would depend on his local measurement, would depend on the past of this particle, but it would not depend on anything that Alice is doing on her lab. And this would be the end of discussion if it was not known that quantum theory predicts some correlations that cannot be decomposed in this way. So this means that you would have the observed probability distributions, and you could recover them from this assumption of a hidden variable by simply integrating over this variable. And well, you know that some correlations just do not admit this kind of formulation. And these are correlations that involve entanglement usually. And this can be more clearly seen through the famous Bell inequalities. And we can, for instance, consider the most famous one, the CH-SH inequality, which imposes an upper bound for the expected expected values that are calculated from these joint probabilities. So what this inequality basically is saying that every classical probability is going to satisfy this inequality. So if I have some correlations that I obtained from my experiment that they can be understood in terms of a hidden variable, they're going to satisfy this inequality. So when you take a quantum correlation that violates this, you know for sure that you cannot understand these correlations in terms of a hidden variable. What you also know is that these correlations, they can only be obtained from a quantum state that is entangled. So what you have here is that this is also a device-independent way of certifying entanglement. Device-independent because I don't assume anything about Alice or Bob's lab. All I get is the joint probability distributions. I compute this quantity and I verify that it violates the classical upper bound. This would be in contrast, for instance, to a device-dependent certification of entanglement. This would be a situation where I don't think that Alice and Bob have a black box in their labs. I assume they have polarizers, they have beam splitters, and I'm using quantum information and quantum theory to construct the shared state. So Alice and Bob are going to perform a bunch of measurements in their lab. They're going to get some outcomes. From that, they're going to reconstruct their state and then do some computation to define if it's entangled or not. So, because I don't assume anything, in this scenario, I have a device independent certification of entanglement, while in the second, I have a device dependent um, certification of entanglement. And what these two scenarios also depict is the level of trust that I have with the labs. So if I don't trust Alice's lab, if I don't trust Bob's lab, and I want to certify entanglement, I should do it this way because then no trust is required. But when you can let go of this distrust, then you can do this in a device dependent way. And this is crucial for many tasks in quantum information where entanglement is a resource that you want to use for some kind of computation. And particularly for cryptography, where you want to assume as little as possible about the parties, such that you can ensure the security of some kind of protocol. But what would you have, for instance, if you have a situation where this distrust between the parties can be lifted at least partially? So you can think, for instance, if you do an online transaction with a bank, uh, you could think that I trust the bank. I trust that's awkward, but I trust the bank's apparatus at least. And but my personal computer might be compromised. So I could have a scenario where I don't want to assume anything about my computer, but I can make assumptions about what the bank's doing because it's trusted. And this kind of scenario fits more into what we call steering scenarios. And steering is this phenomenon that was uh, described at first by Schrödinger in the 30s, in the middle of this whole EPR paradox discussion. And it was also reformulated into quantum information in the quantum information lingo recently. Um, so, what steering depicts is the fact that if you go back to the EPR paradox and the example that I showed earlier, it's not only that by choosing her measurements, Alice can predict Bob's outcome. It's more than that. What Alice is doing is that she is remotely preparing a state for Bob. So by choosing to perform a measurement of spin along the z-axis on her party, depending on her outcome, Alice is preparing a state for Bob. It's going to be either 0 or 1. And this is what, in other terms, this is what EPR called the spooky action at a distance. And this is more of a formalization of this phenomenon. So what is exactly a steering scenario? You have on one side Alice, on the other Bob. They are distant from each other, and they are sharing some quantum state, some source. It's going to distribute it to them, a state rho AB. And Bob does not trust Alice. So he's not going to assume anything about what Alice is doing on her lab. So she is performing some kind of measurements, a collection of measurements M that I can describe in terms of a set of operators that are going to be labeled X by what kind of operation I'm performing, like I'm measuring spin along this or that direction, and A is a label for the outcomes. But I don't want to assume anything about that. So what Alice is doing is going to be described by a black box once again with some input X and some output A. On Bob's side, we know that his reduced state, so if I look only what he's getting on his lab, is going just to be a partial trace over Alice's system. Uh, but the thing is, if Bob wants to condition now his states on what Alice is doing on her lab. So if Alice picks up a phone and tells Bob, okay, for this round of the experiment, I measured X and I got the outcome A. Then Bob can construct his condition states. There's going to be an assemblage of states that is going to be related to whatever Alice is doing on her lab, according to this equation. So the central question in steering is Bob is going to ask himself, okay, this is what I observe in my lab. Did Alice really steer my system? Did she prepare this for me? Or could there be a classical explanation for this? Because it's very different if Alice is doing something on her lab that has a direct influence to what I'm observing in my lab. And another situation that is, well, by calling me and telling me I measured X and got A, Alice is just giving me information about a state that I had all along. There's nothing weird about this. This is something purely classical. So the question of steering is, can Bob understand his conditioned states in terms of some operator sigma that is what we call a hidden state and some hidden variables lambda? So could Bob understand what he's observing in terms of something, some underlying state that was just revealed to him? So Alice didn't steer anything. So from the information that Bob has on his lab, which are these conditioned states, if he can find a model, a local hidden model that obeys this restriction, then he's not convinced that Alice steered anything. But if he cannot find such a model, then he has to admit that something weird is going on. And what you get as a bonus when you certify that steering is taking place in such a way, Bob can also be sure that entanglement is playing a role. So Bob can also be sure that the state that he shares with Alice is an entangled state. So it's easy to see, as we would expect, that bounding locality, entanglement, and steering are closely connected concepts. And in fact, there's a strict conclusion between them. So if we consider the set of all states, you can look at the states that are separable states. And every state that is not separable, every state that is outside this region, is an entangled state. What we know is that all states that admit a model of a local hidden state, that is, the states that you cannot steer, where steering does not happen, they are the separable states are a subset of these states. What this means is, if I show that steering is happening, this means I'm outside this region, so the state has to be entangled. So I can use steering to certify entanglement. And if you go to a region even bigger, you have the states that admit a local hidden variable. That's the states that you cannot use to violate any Bell inequality. So you also know that if I have a scenario that I can use to violate a Bell inequality, if I have quantum correlations, then I must be outside this region, which means the state is also not separable. It's entangled. So what I have here is two situations. There are two ways that I can certify entanglement. If I use a Bell inequality and a violation of this inequality, I am sure that I have an entangled state, but in a device-independent way. Now, if I analyze a steering scenario and I certify that I have steering, I can certify that my state is entangled, but now in a semi-device independent way. So this is a semi-device independent way of certifying entanglement. We also know that when you have steering, you can also certify in this device independent way that the measurements that Alice is performing are incompatible. And what we want to do in this work is go a step further and show, again, in this device independent way, that Bob can learn how many measurements Alice is performing. So by analyzing some quantity sub-object that he has access to in a semi-device independent way, he will be able to infer this secret information about Alice. Um, so how do you certify steering anyway? If you have access to the correlations from the experiment, you can do this in a very similar way to a Bell certification, because there, as you have Bell inequalities, you also have steering inequalities. So these are also some quantities that are upper bounded by some value. And when you evaluate this quantity with the data that you get from the experiment, you can be sure that you are in a steering situation. But what if I want to use only the stuff that Bob has access to? There is a way to also certify steering, not from the correlations, but from the state assemblages for Bob. So after repeating the experiment many times, Bob is going to be able to construct his condition states, his state assemblage. And from this states, what he can do is he can construct what are called the steering equivalent observables. Um, and these observables, for what we care, at least here, you can see them as just some mathematical objects. They are some operators that Bob can construct from only the information that he has on his lab, so only with his trusted information. And the thing is that once you have these observables constructed, if you want to certify steering, it suffices to check that these observables are compatible. Because in this sense, so Bob is going to have access, so he's going to perform many measurements on his states. He's going to condition them on the information that Alice sent him, and he has conditioned states. From that, he can just apply some operators, some things that just a mathematical operation, and then he's going to get from these operations another object, a mathematical object. That's all I mean by constructing. No, these observables, they are really just mathematical. From once he has constructed his, he has characterized his state, he can open a laptop, a notebook, and calculate what these operators are. So at least for what we care, it's just a mathematical object. It's going to be a matrix. Yes, yes, first he measures everything. He's going to determine some expected values for whatever he measured. From that, he can construct what is his state. So, what is the state that is compatible with everything that I observed? And from that, then he can just open a notebook, calculate what are these matrices. And then what he can do is check whether they are compatible or not. And so these it is known that when these steering equivalent observables are compatible, then Bob's state assemblage is unsteerable, meaning steering is not happening. That's not what we have here. There's a classical explanation for what he's observing, and this is a one-to-one correspondence. So if the steering equivalent observables are incompatible, then you certify steering. Okay. And what do I mean by compatibility? So, if you have two measurements, M1 and M2, I can think of them also as some black boxes. So, what a measurement M1 is some box that's going to take as an input a quantum state and is going to spit out some outcome, M1. And if I repeat it many times, I'm going to have some statistics for this measurement. And similarly for M2. So I have two boxes that are describing two different measurements. The question of whether these two measurements are compatible is, could I instead have performed a single measurement G that is going to give me two outcomes, and these two outcomes would reproduce the outcomes from M1 and M2. So if I look at the statistics associated to these two quantities, I could recover M1 and M2. So it's the question of, instead of performing two measurements, could I have performed a single measurement? When this is the case, then I can say that these two measurements, they are compatible. And this notion, of course, generalizes to many measurements. If I have a collection of measurements, M1 to Mn, could I have, instead of performing all these n measurements, could I have performed a single measurement? And from that, could I have recovered my target measurements? When this is the case, I say that this set of measurements is compatible. And the nice thing about this question of compatibility of measurements is that it is a STP-friendly task. So at least by now, I hope some people in this audience already know what's an STP. But for those who are not familiar, STP stands for semi-definite programming. And it's a class of optimization tasks that can be very efficiently solved. So this means that if I have a set of measurements and I want to know if they are compatible, there are efficient numerical methods that are going to answer this question for me. So whenever I have a problem that can be framed as an STP, this is a great advantage. So can we somehow generalize this notion of compatibility to something a bit more broad? So what if instead of trying to recover these measurements by a single measurement acting on one copy of my state, what if I allowed this parent measurement to take not one, but k copies of a state? So now I have a set of measurements that take one copy of a state and spit one outcome, a collection of n of these, and I want to find a way to reproduce them by a single measurement, but now that's going to take k copies of my system. And it's easy to see how whether a set is k compatible is just a relaxation of the usual compatibility problem, because if I take k to be 1, this means that my parent measurement would take only one copy of the state. And in this case, this is just regular compatibility, right? Another thing that I can see, another property of k compatibility, is that every set of n measurements is n compatible. This means that this set can always be recovered by a single measurement that is now going to take n states. So why should this be the case? Because then this parent measurement, what it could simply be doing is I take each of these copies of my state and I'm going to perform one of these measurements on each of the copies, such that I can actually perform all of them simultaneously by performing each one of them in one copy of my state. But anything in between is not known. You have to check. So for k equals 1, it's just regular compatibility. Every set of n measurements is n compatible, but for k between 1 and n, who knows? You have to find out. And the good news is that this kind of question is also STP friendly. So even though it's a bit more complex than just asking about compatibility, asking whether a set is k compatible is something that we can also answer efficiently with numerical methods. This is not the only way that we can generalize the notion of compatibility. So in this case, we generalize the notion of compatibility by allowing more input states to a single parent measurement. What if we now did something different? Now I want to know if could I recover my set of target measurements by performing not one parent measurement, but two. So I have a set of many measurements, and I want to know, could I get away with just performing G and G prime? And from the results of these two measurements, could I infer and recover the results for many other measurements? So this question is a question of whether a set of measurements is simulable. So I have a set of target measurements, M, so it's composed of L measurements. And I want to know if instead of measuring this, could I simulate them by measuring a set n that is composed of k measurements? So what do I mean by simulate and by recover? I have to consider what's the most general way, the most general protocol that I could apply on these measurements such that I could recover these measurements. So mathematically, there's an expression for that, but the intuition behind that is that if I want to recover the measurements of M, I'm going to allow two phases of my strategy. The first phase is a pre-processing that according to some probability P, what I'm going to do is I'm going to choose which measurement of the collection N I'm going to perform. So this is before I do any kind of measurement. I'm going to choose what I'm going to measure, and this is a pre-processing phase. And then I perform the measurement. And after I perform the measurement, according to some probability distribution Q, I'm going to take the outcome that I got from this measurement and I'm going to mix it around. So this is the most general thing I can do if I want to say I can simulate M with N. So whenever I can find these probabilities and a set of measurements that are called the simulators, then I say the set M can be simulated. So this question, the simulability of a set, or we can say the K simulability, if we want to make explicit the number of simulators that I'm allowing, has some important properties for this work. So in general, I want to know, could I simulate this set of N measurements by another set of K measurements? One thing that we see very clearly is that this is also just a relaxation of the usual notion of compatibility. Because if k equals 1, which means I only have one simulator, this is usual compatibility. So we could also think of compatibility as the question of whether can I simulate these measurements with a single measurement. And another thing, and this is the most important for our work, is that every set of n measurements is n simulable. This is also somewhat easy to see because what I'm saying this here is that any set composed of n measurements can be simulated by some other set of n measurements. Of course, you can simulate a set of measurements by themselves. This is a trivial, but it's a valid simulation. So every set of n measurements is n simulable. All right. The problem with the question of simulability is that this in turn is not an STP. There are too many variables, they interact with each other in a way that is just too complex, and there is no known way, at least, of how we can frame this in terms of an STP. So this means there is no non-efficient numerical way for determining whether a set of measurements is n-simulable. However, what we show in our work, the first thing we show is that if a set of measurements is k-simulable, so if it can be simulated by a set of k measurements, then the set of measurement is also k-compatible, meaning I could also recover them by a single measurement that takes k copies of my state as an input. And plus some other details, because we would also know that the parent measurement, the measurement that is going to recover my target measurements, they are going to be separable, which means they're going to have some kind of product structure. And this can be solved with not a single STP, but a collection of STPs still. So what we have here is a criteria for simulability. I cannot test simulability directly in an efficient way. What I can do is perform this other test, and if I get a negative answer, so if I know that my set is not k-compatible with a separable parent POVM, then I know that my set cannot be k-simulable. If you get a positive answer, you don't learn anything. But if you find that the set is not k-compatible, then it cannot be k-simulable. So this is a way to try to go around a restriction that makes this kind of question uh, in practice unsolvable. So we can reframe this in a way that you can answer this in an efficient way. So, what is the final goal of this project? Just to remind you, what we want to do is to find a semi-device independent way of certifying that Alice is performing a certain number of measurements. And we want to do this in a way that we don't assume anything about what Alice is doing on her lab, but we can trust whatever Bob finds out in his lab. And what Bob has access to are his state assemblage, his condition states. So at the end of the day, a trick, a way that we can do to check, to certify the number of measurements of Alice is to see that they are not case-simulable. Because as we just saw, every set of k measurements is case-simulable. So if the set of measurements of Alice is not case-simulable, they have to be at least k plus 1 measurements. And on top of that, they're going to be incompatible. So if I find a way, a semi-device independent way of checking that Alice's measurements are not, say, 3 simulable, I will be sure that she's performing at least 4 measurements. So we check whether they are case-simulable, and if they are not, we can certify the number of measurements. And if they are, we don't learn anything, but at least you have the chance of falsifying this statement and then certifying the number of measurements. So the problem is that I want to know, are Alice's measurements case-simulable? Of course, this isn't something that Bob can directly access, not if he does not trust Alice. So I have to find a way to get this information using only the things that Bob has access to in his lab. So one thing Bob can do is that he can construct the set B, which is the set, the collection of Bob's steering equivalent observables, which are those mathematical objects that Bob can construct using only what he has on his lab. And we also show in our paper that if Alice's measurements are case-simulable, then Bob's steering equivalent observables are also case-simulable. So great, what we did with this step is finding a way that Bob can test whether Alice's measurements are case-simulable in a semi-device independent way, assuming only the things that he has access to. The problem is case-simulability is not an SDP. But we also showed in our paper that if a set of measurements is case-simulable, it's also going to be K-compatible, and the parent POVM is also going to be separable. So instead of testing whether Bob's steering equivalent observables are case-simulable, I can test whether this statement is true. And this is not an SDP, but this statement can be solved with a collection of SDPs. So at the end of the day, what this describes is a method that Bob is going to go to his lab, perform a bunch of measurements, collect the information that is trusted, then he's going to construct some mathematical objects only using the things that he assumes, and then he can perform a collection of simple tests on his laptop to check whether these objects are K-compatible and the parent observable is separable. If not, you can go all the way back in this chain of implications, and you can conclude that Alice's measurements are not case-simulable, meaning you have found a lower bound to the number of measurements that Alice is performing. And that's basically the whole idea behind our strategy. So what we did here is we have found a strategy to certify the number of measurements that Alice is performing in a semi-device independent way. And the nice thing is that these criteria, they can be efficiently implemented with SDPs. So it's something that is not going to grow out of hand exponentially. And along the way, we also devised a way to check whether a set of measurements is simulable, which at first is not a problem that can be solved efficiently, but we devised the criteria that you can at least be sure that a set is not case simulable. And what we expect from this work is that we are going to get uh, perhaps in the future some applications for this in cryptography, because this is one of these scenarios where one of the parties is not trusted. So um, we could expect, for instance, that this kind of strategy could be used, for instance, by a ill-intended party, perhaps some party Eve that is trying to find out some information about the measurements that she wants to hack into. So she could do this kind of analysis to find out information about the apparatus that she's trying to hack into. She could find out how many measurements this apparatus is performing, this kind of stuff. Maybe you could also use this to detect there is some intruder in your network, because this could possibly alter the number of measurements that you're going to perceive. Um, yeah, well, this is the main idea behind the paper, and thank you for listening.
Thank you, Isadora. So do we have questions?
Thanks for the talk. When you mentioned the compatibility, is the same thing that commutativity of the operators?
Well, not in general. So if you go just to regular compatibility, you want to know whether a set of measurements can be reproduced by a single measurement. And you're right, for many cases of interest, this is just checking whether these measurements are they commute. But this only holds for projective measurements. If you go to this more general framework where you're considering non-projective measurements, so you go to POVMs, the commutativity is not a sufficient condition for compatibility. You have to really go in this more general framework.
Thank you.
Thank you.
Thanks for the talk. When you say that Bob doesn't trust Alice, is because of this information, there's A and X that Alice give to Bobby, or is it because of the dependence of the device, or what?
Well, it's just how the scenario is described. But if you recall, what you have in steering is that Alice is trying to convince Bob that she can steer his states. And Bob is looking for an alternative solution. So he cannot trust Alice, because Alice could just be telling him whatever and pretending that she changed his state. But in fact, she's just playing around with the information, trying to fool Bob. So if Bob does not assume anything about Alice, so for instance, he's not assuming she's performing projective measurements or how many measurements she's performing, she could be doing whatever on her side, communicating instead of what she actually measured and the actual outcome. She could be lying, and still he would be able to be sure that steering is or not taking place. Is it, does it answer your question or not so much?
So where entered the the device independence?
So the semi-device independence comes from not assuming that what Alice is doing is just a black box, contrary to what Bob is doing. So I am whatever measurement that Bob performs on his side, I can take into account. So at the end of the day, we say, for instance, that Bob can characterize his condition states. He can only do that because it's not a black box. What he's doing is he's performing measurements, doing tomography, say, And with these measurements that I'm assuming they are known and trusted, then I'm constructing the states. In this sense, Bob is trusted, but Alice is not. Okay.
Maybe.
This one.
Yeah.
Yes.
So let me see if I understand. So like we're basically computing the expectation values of sigma x, y, and z
Yes.
on the marginal state of Alice and Bob, right?
Exactly. Yes.
But this somehow you need to trust what Alice is measuring, because you are saying that she's measuring sigma x, y, or z. So this seems more like an entanglement witness than a steering.
In a sense, yes. Yeah, this is a way of certifying from the correlations. So yeah, you need the joint. You need the joint probability distribution. So we would also get information from Alice. But even if she is lying, if she provides you whatever, you would not have a violation of this inequality, because you could construct a a hidden state model to describe how Alice is lying, such that you get these weird correlations, but they would not violate a any steering inequality.
Okay. The other question is whether you can do the same, like putting a lower bound on the number of measurements in a fully device-independent way. So Bob does not trust itself. Can you also do that?
Hmm. I know. I'm not sure if this makes sense. Like, it's a weird question. Like,
No, I
if
mean, like
I
Bob doesn't trust in itself. Like he just bought a device from the
Mhm.
Chinese, and he's not sure that the device is doing what. I mean, he's not sure if it's actually doing
I see.
projective
Okay.
measurement. So
Okay.
it's not the physicist doing the experiment; it's a user. So
Okay. Sure. Uh. Well, perhaps. I think in.
Rephrase the question. So, what changes basically?
Mhm.
We're discussing. You can discuss other, well, device-independent certification of entanglement, or now you have a slightly different approach here, right? You want semi-device-independent. Is there something that can be generalizable to device-independent case? Something new? I'm not sure that this is the question.
Well,
but,
yeah, I think perhaps, because when you have a violation, for instance, of CHSH inequality, you know that the measurements that you're performing are incompatible. So they must be at least two. Maybe if you find a way to check that the measurements, they, once again, they are case simulable instead of incompatible, that they are not case simulable, maybe you can do something similar. I just don't know how to get this information of like case simulability from the joint probabilities, but that could be a way. Yes, I think. Okay. Thank you.
So I also have a question. It's about, well, so in case of k equals 1, right? So that's one simulability. Or you
Mhm.
have a theorem, a strict theorem that says that, well, if it's not compatible, then there is steering, right? Then that's a certification of steering.
Yes.
So when you go to k compatibility, then this is no longer the case, right? So it's kind of weaker case. And I think, as far as I understood, that the only thing you can tell is, well, get some bound on a number of measurements.
Mhm.
Is that right? I mean, or is this something else you can certify in this way? Well, how does this change with k, for example, if k equals 2 or 3? So what's the difference in this case?
Well, but that's the well, if you check that Bob's steering equivalent observables are not one simulable, what you're doing is you're checking that they are not compatible. And if they're not compatible, you know that you're having steering, because that's the thing about steering equivalent observables. But then you're also checking that Alice is performing K+1 measurements. So she's performing 2 incompatible measurements. And I think it extrapolates in a similar way. If you test that they are not too simulable, it means Alice must have at least 3 incompatible measurements. And that's how it goes. This criteria does not is not able to detect, for instance, if Alice is performing some compatible measurements. If she's performing also some sets of measurements that are compatible already with the others, then this criteria is not going to get it. But they would also not be useful for steering. So
Okay. If there are no more questions, so let's thank Isadora again.